Okay, in this video, let's try to prove the fundamental theorem of calculus for the line integral in the complex analysis. So if capital F prime of z is little f of z, and the gamma is rectifiable, then the line integral f along gamma is f of beta minus f of alpha. Here alpha beta gamma A is alpha, gamma B is beta. Remember that gamma is from AB to C, right? So that's our fundamental theorem about calculus. The integral only depends on the antiderivative plus the initial and end points. Well, this curve or this path is just rectifiable. It's too general. So first, we're going to prove that we can estimate this integral by choosing a proper polygon. Okay, polygonal path. That is the lemma 1.19. Lemma 1.19 says if G is an open set in the complex plane and gamma from AB to C is a rectifiable path, and F from G to C, oh, here is to G, not to C, to G. The image is inside the G. Of course, it's inside C, but specifically it is inside G. F is from G to C is continuous. Then for every epsilon greater than 0, there is a polygonal path gamma, capital gamma, in G such that capital gamma of A is equal to little gamma of A, capital gamma of B is equal to little gamma of B, and the integral of f along gamma minus along capital gamma minus integral of f along little gamma of its value is less than this given epsilon. Okay? This is the estimation of an integral by choosing a better polygonal path. Okay, so this is a very standard method to prove something about the general path. So if you want to show something about the general path, you first choose a nice or better path to approximate the result over the general path, and then you show something about this polygonal path or better path, the path with more properties. Okay, of course this capital gamma depends on this epsilon. Epsilon changes, the polygonal path will change for sure. Okay, proof. This G is very random. It's just an open set. So we are trying to prove the simple case. Case 1, suppose G is an open disk. G is an open disk. why are we interested in this open disk? Remember, we're talking about a polygonal path. How do we construct a polygonal path? Usually, we have several points, and we connect them. Right? We first get several points, and then we connect them. Then this is a polygonal path. But in order to connect them, you have to make sure that this segment is inside G. Right? Not if you just have a general open set, for example, if you have something like this, you have a point here and a point here, you cannot use a straight segment to connect them. You have to have a lot of other arguments. So the open disk has the property. If you have arbitrary 2 points, then the segment between them will be totally contained in this open set. Actually, this is a property of a convex set. Okay, open disk is a convex set. Open disk is a convex set. You only use this property in the following proof. You can actually assume G is a convex open set. I think let's check if it works or not. Okay, convex open set. We have continuous map F from G to C. It's an open set, then continuous map is just continuous map. But if you have a compact set, then the continuous map will become a uniformly continuous map, right? So uniform continuity is better than the continuity because it is more strong, right? So let's see if we can make this continuous uniformly. So how do we do that? So we get gamma. This is trace. Trace is the image of gamma over the closed bounded set AB, right? The trace is a compact. Trace is a compact set. And trace is totally inside the G. So the distance between the trace and the boundary of G. Now this moment we assume this G is open disk. It's going to be strictly greater than 0. First, the intersection is empty. And because it's compact, then the distance will be strictly greater than 0. Remember that if you just have two closed sets, okay, here let's mention some small topology. If A, B are closed and A intersect B is empty, then the distance between A and B is only greater than or equal to 0. It's just greater than or equal to 0. It could be 0. How do we know that? Think about the asymptotes. Right? Asymptotes. So this is a closed set. The x-axis or y-axis is also closed set. They are disjoint, but the distances will be eventually equal to 0, even though they are disjoint. All right? So if you just have two closed sets, this distance is greater than or equal to 0. But if one of them is compact, this is compact, this is closed, this is compact, then this distance will be strictly greater than 0 if they are disjoint. This topology is a property of a compact set. Every open cover has finite subcover stuff. Okay, so since it is strictly away from the boundary, it follows that if G is a slightly smaller open disk, then this trace is totally contained in the if G is this open disk, then the trace will be contained in the a slightly small disk, 1 beta, where beta is where not 1, where not beta, rho, where rho is equal to this radius minus 1/2 the distance gamma and the boundary of G. Okay, just remove a little bit of different distance. Okay, so we can shrink this G a little bit so that still this this trace is inside the smaller disk, but this whole smaller disk is inside the BCR. BCR is G. It's a compact set. The reason we want this smaller closed disk inside the open disk is that whenever we take the closure, it's compact. And F, remember we are only interested in the integral of F along gamma. So F is uniformly continuous on this rho, on this compact set. Okay, so we just need the uniform continuity. Okay, so without loss of generality, we can assume that F is uniformly continuous. Right? So originally we only know F is where's F? F is continuous, but now let's assume F is uniformly continuous by shrinking the domain a little bit. Okay, so let's see. We have several stuff. So AB disk G, trace gamma, complex plane C, F. F is uniformly continuous. This is uniformly continuous because we get a compact set. AB, of course, bounded closed is compact, so gamma is uniformly continuous. Gamma is also uniformly continuous because its domain is naturally compact. Okay, so for any epsilon, remember, epsilon is in the range of F. For any epsilon greater than 0, you can find a delta greater than 0 inside the domain of F, so that whenever a pair of a point has distance less than delta, the image will have distance less than epsilon. And then for this delta, we can go back to the closed interval AB because of a uniform continuity. You can say delta, let's see, we can say there exists a delta prime greater than 0 such that whenever a pair of a point is less than, a pair of a point has distance less than delta prime, the image of this pair of points will be less than delta. Okay, so from epsilon, you get a delta. From delta, you get a delta prime. All right, so you have two uniformly continuous functions. Okay, let's write it down. So, given epsilon greater than 0, there is a delta greater than 0 such that whenever z minus w less than delta fz minus fw ops value less than epsilon. All right, so that's uniform continuity for f. And there is a partition. There is a partition T0 less than T1 less than T2 less than Tn of AB. So we're talking about the partition AB such that gamma s minus gamma t will be less than, okay, gamma s gamma t will inside the G will be less than delta whenever tk minus 1 less or equal to s pair st less than or equal to tk. Okay, so you have a partition of AB so that each subinterval will have length. Here the norm of a partition will be less than delta prime. The norm of a partition will be less than delta prime, so that whenever you get a pair of a point from one single subinterval, they are close enough so that the image will be less than delta. Okay. And also, remember, this is one condition. We want to guarantee the image of gamma s gamma t less than delta. And also remember, we have the integral. The integral is about f gamma, right? So, and such that for any tau k inside tk minus 1 tk, we have ops value integral f gamma minus sigma k from 1 to n f of gamma of tau k times gamma of tk minus gamma of tk minus 1. Ops value less than epsilon. Okay, so this is from the definition of integrability of f. Definition of integrability of f. So you need a better enough partition so that it satisfies this condition, it also satisfies the uniform continuity. Okay? You first get this one, and then you get uniform continuity for the second one, and then you join them, get the refinement. It will satisfy both. Okay, good. So now we have several points, T0, T1, T2, T3, up to Tn. Okay, so here we have tk minus 1 and tk. It is a one subinterval. Okay, for this subinterval, this is a gamma of tk minus 1. This is a gamma of tk, and we're going to use straight segment to join them. This segment is define capital gamma from AB to C by capital gamma of T is equal to tk minus T over tk minus 1 times gamma of tk minus 1 and plus T minus tk minus 1 over tk minus 1 and gamma of tk. Okay, the linear combination of these two endpoints. You check that when t is tk minus 1. When t is tk minus 1, this term disappears. You get gamma tk minus 1. when t is tk, the first term disappear, you get gamma tk. And this is linear function, so it is the connection. Okay, so for k equal to 1, 2, 3 up to n, for each sub-interval, we define this capital gamma t by this segment. So we do have a connection like 1, 2, 3, 4. We will connect these two, these two, these two, like the gamma t0, gamma t1, gamma t2, and gamma t3, something like this. This is the polygonal path, and we are going to show this polygonal path satisfy our condition. Okay, so let's emphasize capital gamma of t traces the straight segment from little gamma tk minus 1 to little gamma of tk. Capital gamma is a polygonal path in G. It's a polygonal path in G. And let's see one computation. Capital gamma, you see, this is gamma of t. This is capital gamma of t. Correct? And there's some place you have a gamma tau k. Gamma tau k. Some point. We want to know the distance between these points, like gamma tau k of capital gamma of t for whatever point from this interval. Let's check. Well, check here. This sum is 1. This coefficient, I'm talking about the coefficient. This coefficient plus this coefficient is exactly 1. So let's, and also they're positive. Tk minus t over tk minus tk minus 1 and t minus tk minus 1 over tk minus tk minus 1. Both are positive between 0 and 1. Okay? So here this t is between tk minus 1 and tk. Okay, so let's check. We get tk minus t, tk minus tk minus 1, gamma tk minus 1 minus gamma of tau k, and plus t minus tk minus 1 over tk minus tk minus 1, gamma of tk minus gamma of tau k. Okay, so subtraction, this subtraction, if you combine the coefficient, that's exactly the gamma tau k. And the first part is capital gamma t. And then you apply the triangle inequality. So this is a positive number. You can move this positive number outside. And this ops value gamma tk minus 1 minus gamma tau k, and plus, this is also a positive number. Gamma tk minus gamma tau k. And then we're going to use this property, the property that whenever you have a pair of a point from one single subinterval, then the ops value of the difference will be less than delta. Okay, so this one, these two, this is one of endpoint. This is arbitrary point from the interval. So they are both selected from one single subinterval. So it's less than the first stuff times delta and plus the second coefficient times delta. And this, the sum of the coefficient is 1, so it's less than delta. It's equal to delta. So that's t less than or equal to tk minus 1 less than or equal to tk. So that is the reason we get the ops value of capital gamma of t minus gamma of tau k is less than delta on page 66, how we get it. Okay, so it's a very interesting computation. Okay, and then remember we're going to compare the integral of f along original gamma and the integral of f along capital gamma, polygonal path. Let's compute what is integral of f along capital gamma. Capital gamma is a polygonal path. It's piecewise smooth. So okay, so we integrate over each part. And then for each part, remember we know f gamma t d gamma tt from tk minus 1 to tk. And this gamma is a linear function. It's smooth, so it is equal to f gamma t and gamma prime of t dt. What is gamma prime? Here is a capital gamma. Here is a capital gamma. What is a gamma prime? You differentiate t, then this part you have a -1 with this coefficient. Here you have a positive with this coefficient. So you will have integral from tk minus 1 to tk f and gamma t and the capital gamma prime becomes gamma tk and minus gamma tk minus 1 tk minus 1 dt. Okay, so this is the derivative of capital gamma prime. Okay, this whole thing is a derivative capital gamma prime. This is a coefficient negative sign, coefficient positive sign. All right. Okay, now let's this is integral. Now let's try to compute integral ops value of integral f along gamma minus integral of f along capital gamma. Okay, this ops value, the ops value of the difference is, I'm going to insert what? Insert this stuff. I'm going to insert this. So we get what? Minus sigma k from 1 to n f gamma tau k and gamma tk minus gamma tk minus 1. And of course I'm going to plus this and then minus f, the integral of f along capital gamma. Integral of f along capital gamma is sigma k from 1 to n, integral from tk minus 1 to tk, f capital gamma t, and this ratio, dt ops value. Okay? I just copied here, So we insert it, so still we have equality. And then we apply the triangle inequality. Once we apply the triangle inequality, the first part will be less than or equal to epsilon. Actually, strictly less than epsilon. And plus ops value sigma k from 1 to n. And this one is constant. gamma tk minus gamma tk minus 1. Here we have gamma tk minus gamma tk minus 1. So we factor out gamma tk minus gamma tk minus 1. Both terms have this. And this one, it's a number. A number, here it has denominator. If I factor out, brutally factor out the denominator, it becomes the first term. The first term has no such denominator, so it's kind of we multiply top and bottom by the denominator, so it becomes this term times tk minus 1. It is the integral of tk minus 1 to tk, the constant value. Okay, so remember that the integral from a to b k dt is k times b minus a. This multiplication by the difference is equal to the integral of a constant function. And the minus and this part, f capital gamma of t dt. Here there's a big parenthesis, ops value. This ops value is corresponding to this ops value sign. Okay, and then we're going to move this into the integral. Remember, we're going to move this ops value into the integral, into the sigma. So it's less than epsilon plus sigma k from 1 to n. Here we have ops value gamma tk minus gamma tk minus 1. This is a positive number, so we don't have to put ops value. And this one, we continue move it into the integral. And dt. Okay, so first we pass the ops value to the into the sigma. That's the triangle inequality, and then we pass it to the integral inside of the integral. Okay, and this absolute value we just verified here. T is always between tk minus 1 to tk, so this is gamma t minus gamma tau k is always less than delta. Remember, once the distance is less than where I have it, once the distance is less than delta, then the fz minus fw is less than epsilon. So this term is less than epsilon. It is less than epsilon. Okay, because this input, the pair of the input is less than delta. While it is less than epsilon, integrate epsilon, you get the epsilon times tk minus 1. And cancelled with this tk minus 1, you only have epsilon. Okay, so it's less than epsilon plus epsilon sigma k from 1 to n ops value gamma tk minus gamma tk minus 1. What is this? This is a variation of gamma with respect to this partition, and we know this gamma give us a rectifiable path, so it has bounded variation, so it's less than or equal to epsilon 1 plus total variation of a gamma. Okay, so what do we prove? We prove that this ops value of the difference is less than epsilon times 1 plus total variation of gamma. Of course, we can modify the epsilon a little bit to cancel this coefficient. So basically, we finished the proof of part 1. In this whole part, what kind of property do we use? What kind of property do we use? We only use, you have 2 points, you can connect them. That is convex set, the property of convex set. And this part, yeah, here we are going to connect, we're going to use a straight segment to connect 2 points, gamma tk minus 1 gamma tk. This is a convex set. That's why we say, I said at the beginning, we can assume G is just a convex set. And in this place, the boundary of G, we don't need the property boundary of G is a circle. We only need the trace of gamma is a compact set. This is a closed set, that's enough. So again, the case 1 works for all convex open set, not just a disk. It's not just a disk. Okay. Okay, very good. So we finished the first case. G is an open disk. Now let's pass to the general case. G is arbitrary. G is arbitrary. G is arbitrary. Still, the trace of gamma is compact. So we're going to cut this gamma into small pieces. Okay? Then there is a number R with the property that the R is smaller than the distance between the gamma and the boundary of G. Okay, and choose a delta greater than 0 such that whenever S minus T less than delta, the gamma S minus gamma T is less than R. This is uniform continuity of gamma. Okay, uniform continuity of gamma. Okay, so again, remember that we are trying to cut this gamma into small pieces. Each piece is contained in one open disk. So let P be a partition of AB. B, a partition of AB. With what? With the norm of the partition is less than delta, small enough. Okay, and when this happens, then the gamma T minus gamma TK minus 1 will be less than R for T greater than or equal to gamma TK minus 1 less than or equal to TK. So in a small interval, every point T here, this is gamma TK minus 1. And you just get an open disk. The gamma T is always inside this open disk with the radius R. Right? So that's a demonstration of this the sentence. So the gamma K from Tk minus 1 to Tk to G, if is defined by gamma K of a T to be is equal to gamma of T, then then this gamma k, the trace of gamma k will be totally contained in the disk centered at gamma tk minus 1 with radius r. It's open disk for k greater than or equal to 1, less than or equal to n. So we cut it into n small pieces. Each piece will be inside the open disk. Then by case 1, there is a polygonal path let's call it capital gamma k from tk minus 1 to tk to g or to this open disk, such that capital gamma k of tk minus 1 is equal to gamma k of tk minus 1, of course is equal to gamma tk minus 1, and the capital gamma k of tk is equal to gamma of tk. The same thing, just connect. When you have this curved path, you just connect it this way. But eventually you will connect the initial and terminal points. Okay, and because you have this mount, you have the partition first. You have a partition, then you have gamma k. When you have a gamma k, you have capital gamma k. So when you study capital gamma k, this number n is already known. This number n is already known. So we can assume this f along capital gamma k, the integral of f along capital gamma k minus integral along little gamma k, up's value is less than epsilon over n. This n is known, is fixed. It does not grow to infinity. All right? And this capital gamma k is defined for k between 1 and n. Then define capital gamma of t equal to capital gamma k of t for t between tk minus 1 to tk. Then by the triangle inequality, we have integral f along capital gamma minus integral f along little gamma is going to be less than epsilon. Correct? So that's our proof. That is our proof. Right? So we finish the proof of the general case when we have a general open set G. When we have general open set G, we just cut the domain of a gamma into small pieces so that each piece is mapped into an open disk. It's like when you have AB this way, it's mapped, the trace is like this. Then what we do is the following. We just use open disk, open disk, open disk, open disk, open disk, open disk. A chain of open disk to cover it like this. Right? Okay, so anyway, we finished the proof about the approximation of an integral by choosing a proper polygonal path. What is the advantage of polygonal path? It is piecewise smooth. Okay, polygonal path is piecewise smooth. That's a property we use. Okay, now let's back to the proof of a fundamental theorem of calculus. Proof of theorem 1.18. 1.18 again. It's like this. It's like this. We also have two cases. Case 1, gamma from A, B to C is not just rectifiable, it is piecewise smooth. piecewise smooth, then the integral f along gamma is equal to integral from a to b f of gamma of t d gamma, and you can pass this gamma forward. It's f gamma t f gamma and gamma prime of t dt, and the little f is capital F prime gamma t gamma prime of t dt, and you use a chain rule, you have integral from a to b f compose gamma of t, the whole thing prime dt. And this is an integral with real variable, but it has two components, the real and the imaginary component. But anyway, the integral is separate. You have integral along the real axis, you have integral along the imaginary axis. So we can still apply the fundamental theorem of calculus, FTC, fundamental theorem of calculus. It is f of gamma b minus f of gamma a. Gamma b is beta, gamma a is alpha. So we have this. So we finish the proof. When you have an even better gamma is piecewise smooth. In the general case, gamma is just rectifiable. Gamma is just rectifiable, then given epsilon greater than 0, there is a polygonal path capital gamma such that the ops value integral f along little gamma minus integral f along capital gamma is less than epsilon, based on the above lemma. We have this, and we know this polygonal path is piecewise smooth. This integral is equal to capital F of beta minus capital F of alpha, because gamma A is gamma A and gamma B, capital gamma B is a little gamma b. Okay? Because capital gamma is piecewise smooth. All right, so what do we get? We get ops value f integral f along gamma minus this difference can be less than arbitrary positive number. Epsilon is arbitrary, yes. The difference can only be 0. So the difference can only be 0. We get it. All right, so excellent. So we finished the proof of fundamental theorem of calculus for the line integral in the complex analysis. All right, okay, excellent. So we finish this lecture and we will continue the discussion in next lecture. Thank you very much.